Hi everybody, let's go over the practice test. Okay, so you should have out the exponential functions practice test, and we're going to start by reading question 1 together. It says the population of a city is growing at a rate of 20% per year. The population in 1940 was 40,000. So I can see that my initial amount is 40,000 and my rate is 20%. Now I also see the word growing, so that tells me this is going to be an increase. So I know I'm going to be using the function y equals a times 1 plus b raised to the x power. But I know that when I put in my rate of change into the formula, it's going to need to be a decimal. So I'm going to go ahead and convert 20% to the decimal version of itself, which is 0.20. That means my answer should be y equals 40,000 times 1 plus 0.2 raised to the x power. Now, there's a nicer way to write this. We can make this even more simplified, which is y equals 40,000 times 1.2 raised to the x power. And that's the function of the population over time. Now, since x represents years, and they're asking us about the population in 1998, we have to take into consideration what time 0 is. So x equals 0 is 1990. So how many years later is that? Well, in 1998, that would mean 8 years later. So we're going to evaluate the function at y equals 40,000 times 1.2 to the 8. So in my calculator, I would put in y equals 40,000 times 1.2 to the x if I was going to look at the graph. Or if I'm just going to evaluate, I would just put in this part into the calculator section, and I would put in this answer. Let's see what you would get. So depending on how you input this into the calculator, you either got this answer, so 85,996.3392 people, because it's population, or you input the function into the table and you saw this value, in which case you'd say 85,996 people. Now they didn't put the decimals in here because it doesn't have enough space. So the question is, what do you put down? How do you get the right answer? Well, you have two options. I mean, since we're talking about population here, we wouldn't want to have 0.3 of a person. So the answer I'd be looking for is 85,996 people. Well, that's a good approximation of what the population would be in 1998. Okay, now let's move on to the next question. It says Sam invested $500 into a savings account. So a savings account is telling me his money's probably growing. And it's growing at a rate of 12% each year. How much money would he have at the end of 5 years? So this is another case where we're looking at a percentage growth. So I know I'm going to be looking at y equals a times 1 plus b raised to the x. Okay, so my amount of money, my initial value is $500, and my interest rate is 12%, which as a decimal is 0.12. So the function that would represent this would be y equals 500 times 1 plus 0.12 raised to the x power. Or if you simplified it, y equals 500 times 1.12 raised to the x power. Now, again, I could put this function inside of my calculator and graph it and look at the table, or I could evaluate it at any number. Now, it turns out that they like us to find how much money would be in the account after 5 years. So that's what I'll be replacing in for the exponent. So if I have y equals 500 times 1.12 raised to the 5th power, what would the calculator give me? Well, let's see. Okay, so if I put into the calculator just this part, so 500 times 1.12 raised to the 5th power, it tells me $881.170846. Or I could look at the graph and the function and scroll down to 5 years and see 881.2. So what value do I put in? In this case, they're talking about money, so you should evaluate this in terms of money. So I would say that the answer is approximately $881.17. So I'm truncating it right here. Okay, let's move on to our next problem. Let me go ahead and take these guys out of here. Okay, our next question says, two students were asked to find the value of an account after investing $500 for 5 years. The account is growing at 2.5% per year. Student A said f of x equals 500 times 1.25 to the fifth. And student B said f of x equals 500 times 1.025 raised to the fifth power. First, they want to know whose equation is correct, what mistake did the other student make, and then using the formula, find the value of the account after 5 years. So actually evaluate whichever one is correct. Okay, first of all, let's pull out some key information. So I know the initial value is $500. I'm going to evaluate it after 5 years, so my exponent should be 5. And my growth rate is 2.5%. Now, since it's an investment and it's growing, I'll again be using y equals a times 1 plus b raised to the x power. So the question is, which of these students correctly input those values? Well, both students, as you can see, have the right initial value, and both have the correct time. So x is 5 years, but the rates of change are different. So the big question is, what is 2.5% as a decimal? Well, here's what I know. b equals 2.5%. And if I want to turn this into a decimal, I must move this decimal place to the left 2 times. So let's do that. 1, 2. So that means my new decimal place will be 0.025. That means that student B is correct. Now, what mistake did student A make? Because student A is the one who made the mistake. Well, they incorrectly converted the percent to a decimal. They only moved the decimal place once, not twice. They only moved the decimal place, that's his decimal, the decimal place once. Okay, so using the correct formula, find the value of the account after 5 years. Let's see what happens when I input this into the calculator. Okay, so I put it into the calculator, and here's what I got. 565.70411064. So I put it right into the calculator section. Notice there's no y equals here. So the question is, what number do I put down for my answer? Well, again, we're talking about money here, so it makes sense to round this to the nearest hundredth place. So I'm going to go ahead and take that amount, check to see if this value, the 4, does not have me round. It would only round up if it were a 5. So my answer would be that the student would have $565.70 after 5 years. Okay, let's talk about question 5A and B. Now, in both of these questions, they're asking you to find the point of intersection. And what we did is we showed you how to use your calculator, so that tool, to find the intersection of 2 points, the intersection of 2 functions. What we have here is an exponential function and a linear function. An exponential function and a linear function. I want you to visualize what that might look like. A linear function and an exponential function could never cross. They could cross once, or they could cross twice. So that's what we're looking for, and then we're going to use the powerful calculator to calculate the intersection. So I'm going to go ahead and show you what I got in my calculator, and then we'll write down what the point of intersection or intersections is. Okay, so I put the 2 functions into my calculator, and this is what I got. So here's my exponential function, and here's my linear function. And as I can see in this case, they intersected once. So I went in and I pushed the calculate button, well, second and calculate. I scrolled down to intersection. I chose the 2 curves. I guessed where the intersection was right there. And here is what I got. So I found that the intersection point was approximately at this x value and this y value. So my answer for my intersection point, and I only have one answer, is 0.83 for my x value and negative 2.50 for my y value. So that is approximately the intersection point for A. Okay, let's try that again for x. Let me get this guy out of here. Okay, let's try that one more time. So I'm going to go ahead and I'm going to input these two functions in my y equals section of my graphing calculator graph, and then we'll see where those intersection point or points are. So when I input those two graphs, those two functions in, here's what I found. I have my linear function and my exponential function. Here I can see there are clearly two intersection points, so I'm going to have to do calculations twice. So here's what happens the first time I did my calculation. As you can see up here, I guessed around this point, and they gave me this intersection point. So the top point I got for my x value is 3.25. So I'm rounding right here, 3.25. And my y value is 9.49. So that is, again, the top intersection point. Okay, let's get that bottom one. Okay, the bottom intersection point is approximately at these two locations. So my other guy is at negative 1.30. Notice that that 6 is rounding the 29 to a 30. And then 0.41. 0.41. So those are the two intersection points for my second function, for my second two functions. Okay, let's take a look at our next question. So let me move our stuff up. Here we go. So it says, write an equation for the graph below. So here's our graph. And the first thing I always do when I have a graph is I organize some of the points into a table. So the first obvious one is the point 0.3. And there's another point up here at 2.12. But I want you to notice I'm leaving a space because it's pretty obvious that there's another point at 1.6. Now, once I've recorded those points, I'm ready to look for the important information I need. So I know this is an exponential function, so it's going to look something like this, y equals a times b to the x, where a is the initial value, and b is the change that's happening from our y values. Now, clearly our y values are growing. I can see that from the graph and from the table, but by how much? Well, there looks like they're multiplying by 2 each time, which they obviously are. So that means that my function would be y equals 3, that's my initial value, times 2, that's my multiplier, my rate of change, to the x power. That's the function that would represent this graph. Now let's look at our next question. Write an exponential function for the given table. Now this is almost faster. I don't have to go from the graph to the table. I already have the table. So first, what is my initial value? So my initial value for y equals a times b to the x, my a is going to be 3.5 because that's my y-intercept. And then I ask myself, what is my change from 3.5 to 7, from 7 to 14, and from 14 to 28? It's times 2 again. It's doubling. So my multiplier is 2. That means that my answer would be y equals 3.5 times 2 raised to the x power. And that's the function that goes with that table. Now the very last thing that you were asked to do was to tell whether a function was linear or exponential, and then write the type of function next to the story. That's it. You just had to write linear or exponential. So the big question is the change adding or subtracting? Okay, so if it was adding or subtracting each time, then it's linear. And if it was multiplying or dividing, then it was exponential. So I have to read the story to figure that out. Here's our first one. Mary pays $4 to go to the fair. So Mary pays $4 to go to the fair and $1 for every hour at the park. Now, maybe you're not totally seeing this yet. I don't know if I do. So I'm going to have x be my hours, so 0, 1, and 2. Let me see if this makes sense. Okay, so she goes to the fair, so she pays $4 to go to the fair. And then every hour she has to pay $1. So an hour goes by, so now she's paid a total of $5. $4 to go to the fair and $1 for parking. Okay, how about after 2 hours? She paid $4 to go to the fair, $1 for the first hour, $1 for the second hour. She's looking at $6 total. So when I look at the table, I can clearly see that the change in this case is +1, +1. That means that this is a linear function. So for me, I like to organize my verbal story into a table to figure out what's going on. Let's read letter B. The rhino population is decreasing at a rate of 2% every year. Okay, this one's obvious. If something has a 2% change, then that means that we're going to have to multiply to find what that change is. 2% of something is only found by multiplying by that percentage. Well, this is going to be a rate of change that's a decay. So because I see that the change has a percentage, I know that this is exponential. Okay, let's look at letter C. A car is driving 35 miles per hour down the 5 freeway towards San Ysidro High School and is pulled over for driving too slow. So they're going 35 miles every hour. Let's check. Okay, so 1 hour has gone by, they've gone 35 miles. 2 hours have gone by, they've driven 70 miles. 3 hours have gone by, they've driven 105 miles. Clearly, they're adding 35 each time. That means this is linear. Last but not least, a car is getting ready to race. Here's the car's speed with time. First and foremost, in order for this to make sense, can you cross this out for me? I'm realizing this doesn't make sense, so cross that guy out. Okay, so let's take a look at the time and the speed and see how it changes. Okay, so at 1 second, it's 5 miles per hour. At 2 seconds, it's going 15 miles per hour. 3 seconds, 45 miles per hour. 4 seconds, 135 miles per hour. What is the change for each second? It's clearly times 3. Multiplying and dividing is an exponential function. And that is our last problem.